Okay guys, so welcome back to this online lecture for ME501. So here I just wrote what we did basically in the last two lectures. We started by looking at the numerical solution for first order differential equation, and we look at the Euler's method, modified Euler's method, which is the midpoint, the Eun's method, and the Runge-Kutta. And basically I give you the codes, the MATLAB codes for each one of these ones. Okay, so today we're going to do another method a little bit more detailed, but as an assignment I'm going to ask you actually that you will have to be the one to write down the function, okay, or to do the little programming. Alright, so let's start with this new method, which is called the Richardson method. Okay. So there are instances in which the nature of the governing equation in the initial value problem for instance, okay, let's look at three cases. The function fy of t exhibit large variations in a very short time. Okay, this is the case we're going to study into more detail. So the second case might be that it's highly nonlinear, which to a certain extent is related to the first one. Okay. So in these instances, the numerical solution may require extreme resolution. Of the time step. Okay, so basically it means that if you have a large variation, let's say you go through a curve and then this curve goes up very quick, if your time step is not small enough, you won't be able to capture the change, the rapid change in the direction, if you want, or the rapid increase of the function. So that's what is meant by extreme resolution. Okay. Which unnecessarily slows down the solution process in regions where it's not necessary to have such requirement. Okay, so once again, to make this clear, imagine you have a function that initially it goes like small variation, let's say it goes straight or just small variation, then backs up, so, and then let's say it goes back slowly down to the initial value. So in this area here, you don't need a very small time step because the changes are very small, but then you need a very small time change when the function goes up, and again, you don't need such a small time step when the function starts going down because it is smoother. Okay, but so if you select a very small time step, you're going to slow down the numerical process. All right, so a technique known as the Richardson extrapolation can be employed to perform adaptive time stepping for error control. So basically your time stepping needs to be based on something. So on what it will be based is on error control. So the idea is to compute two estimates of the solution at time step n+1. Basically, just to give you an idea, what we do here is that in order to predict a certain error, we need to have a solution at a certain time step, and we do that for a certain time step, let's say delta t. We calculate the same solution at the same time, but for a different time step, and we compare the two solutions. And then you will have some criteria for the error. If it's not satisfied, you have to do the adaptive. If it's satisfied, you just keep going with the solution the normal way. Okay? All right, so time steps. So the first case will be here. First one is using a full time step delta t. So doing this, you're going to calculate yi plus 1 of t. So you want to call this one of 1 to make a difference. Will be y of n plus 1/6 of k1 plus 2k2 plus 2k3 plus k4. So basically this is the normal rule ejecuta, okay? But you calculate it at the time step using the time step delta t. So first one here, you want delta t1 equal to delta t, okay? And you do this calculation using delta t1. All right, now we need to find a second estimate in order to estimate the error. Okay, page 133 and 2. Now we'll be using time step that will be half the previous one. So using two half time steps. So basically that only means that our second time step delta 2 will be delta t divided by 2, okay? Which will be delta t1 divided by 2. That will be the same. So now using that relation, using delta t2, we can calculate y n plus 1/2 time step of 2. This will be equal to what? Y of n plus 1/6 of k1 plus 2k2 plus 2k3 plus k4, okay? Okay, so this is the half time step. Now we know that y n plus 1 of 2 will be equal to what? The y n plus 1 half, the previous one we just calculated, plus 1/6 k1 plus 2k2 plus 2k3 plus k4. Okay. Let me add one thing to differentiate these two over here. So maybe we can put here for the first time step, we can do the little one over here. So at least it's clear, it's over there. And for this one over here, we can just add the little 2 over here. It's not necessary, but it's just to show that this case over here, do you remember the function of delta t? You need to calculate them, evaluate them using this this time step. Okay? All right. So now that we know this, we can estimate what would be the error. So then the error band, just the error between the two estimates is what? So we'll have the error over here is equal to 2 to the n divided to the 2 to the n minus 1. So this n minus 1 is like this, to the minus 1. It's not to the power, times y n plus 1 2 minus y n plus 1 1. So this is the error estimate. So this is on which we're going to base if we need to do the adaptive time step or not. So basically, if again, imagine we have a function that goes straight, so error will be very small, so the adaptive time step is not required, then this will spike up going up. In that case, the adaptive time step should kick up, and then this error will be large, so you have to redo the time step. And then again, in here, let's say the time step will be appropriate, and you don't have to do the adaptive time step. Okay? So in that equation where n over here is the order of approximation. So in other words, in this case, n equal 4 if we use the Runge-Kutta approximation. Alright, so in that case, let's see what would be the expression for the error. Will be error Runge-Kutta will be 2 to the 4 divided by 2 to the 4 minus 1 times y n plus 1 2 minus y n plus 1 1. Alright, so basically at the end we have that the error for Runge-Kutta, which is the one you will have to program, will be equal to what? 16 over 15 error at y n plus 1 2 minus y n plus 1 1. Okay, so this is actually the one you will have to use when doing the programming. Okay, so basically so far, let's go back. When you do the programming, what you need to do is you select a certain time step, okay, delta t. Then you calculate the first approximation, k1, k2, k3, k4. You can use the OD files, will be the same thing over here, okay? You can use this one over here, basically will be the same thing as OD4, but with a time step delta t, okay? Now, you use the second approximation, which is this one, the one here at the top. So again, this is the Runge-Kutta approximation, but this time with the time step half of the previous one. You take these two solutions, okay? And you take these two solutions, you do y2 minus y1, you divide by, oops, over here, you do this 16 over 15 y2 minus y1. So depending on the error, either you don't do anything, you just say that the solution will be the normal one, or you will have to do the adaptive, okay? But before we go to that step, I'm going to do a middle step over here. I'm probably going to do it in a different color, so that you see it's not part of the procedure. I use this purple over here, okay, and then we follow in blue and black with a normal procedure. Okay, here I just need to develop one little thing. All right, so now let us use the above expression to estimate the necessary time step delta T max to achieve a prescribed tolerance. So for instance, you know that if you have a problem, you don't know what the final answer is going to be, but you can set up a tolerance. Let's say you want your results to be 10% accurate. So that would be what? 0.1. Okay? Now you want your result to be 0.01 accurate, okay, or 0.001 accurate, okay? So prescribed tolerance epsilon of the solution error, which is basically the equation we have over here. All right. So basically what's going to happen, this is defined as delta T max needs to be equal to delta T. I'm not going to go into the details of this stuff. 2 and minus 1. But basically what we do is you take this expression in reverse, okay? We reverse this expression here, okay, for the time step. So you're going to get over epsilon y n plus 1 to the 2 minus y n plus 1 to the 1, and this is to the power of 1 over 1 plus, so this is let me change it, is n plus 1, but I put 1 plus n, okay? Alright, so that means, again, let me go to the next page. So this will be page 134. Okay, so that means that now we're going to need this solution here. I'll go back in black. So for Runge-Kutta, which is what I've been calling RK, we're going to have that the delta T max for Runge-Kutta will be what? Delta T over 2 to the 4 minus 1 divided by 2 to the 4 times epsilon to the y n plus 1 2 minus y 1 n plus 1 to the 1 over 1 plus 4. Okay? So basically that means that the error at the end is equal to, so it's equal to what? Delta T of 15 over 16 the tolerance y n plus 1 2 minus y of 1 n plus 1. Okay, and this will actually be equal to delta T of, and this will be 1 over 5 of what? If you remember from the previous page, this error function here was 16 over 15 y n plus 1 at 2 minus y n plus 1 at 1, which is just the inverse of what we have over here, okay? 15 over 16 and this one. So we can simplify that equation over there as being equal to the epsilon divided by the error, everything to the 1/5. Okay? So this is what needs to be done during the programming. But again, I'm going to give you hints on how to do it. Alright, so let's put over here. So that means that therefore at this point an initial time step, so you can start with a certain time step. Alright, let's say delta t equal to whatever, 0.1. Therefore, initial time step delta t and a prescribed tolerance epsilon here can be set up so therefore initial time step delta t and a prescribed tolerance epsilon can be set up to determine if adaptation so basically make the time step smaller is necessary. Okay, and this needs to be done at every time step. Alright, so alright, you determine the error, you have the delta t, you have the delta t max, you have the error. Okay, so now we can keep going with the programming. So now, if delta t max Rungecuta, the one we use over here, is higher, than delta t, tolerance, so this is delta t, is satisfied, okay, and no adaptation is required. So basically that means that we just have the traditional ODE4, okay? And in that case, you calculate the solution as y n plus 1, will just be equal to the y n plus 1 using the delta t because adaptation was not needed, plus the error of the Rungecuta. Okay? So this is, so you do the programming, at each time step you do this, if you find that the error, which is what? If you go back, the error is in function of y, okay? It's yn plus 1 at 2 minus yn plus 1 at 1 divided by 16 over, so it's 16 over 15, you use this one. So once you replace this value here into here, and you calculate this time step, and you find out this, no adaptation is required. Now, in the other case, so if this is not happen, else, if you want, I do the programming here, if you want the loop, if this, all right, if this satisfies, you do this, else, okay, trying to do the logical programming, else will be delta t max Rungecuta is more than delta t. In this case, tolerance is not satisfied and adaptation is required. All right. So in that case, what do you do? Okay, so we need to define a new time step. So the first thing you're going to do is subdivide the current time step Okay, so imagine you do time step 1, 2, 3, 4, 5. You don't need adaptation, and then between 5 and 6 you need adaptation. So you need to break the step 5 and 6 into, let's say, two more intervals. Okay, subdivide the current time step into ns sublevels or intervals. Okay, so how many? That's what we're going to do now. So you have ns, the number of intervals that you need, will be equal to delta t over delta t max plus 1. So obviously you need to make this a whole number. Okay, you cannot take 2.3. So I'll show you. I think you use the floor, okay, of this ratio, and you add 1 to it, okay, when you do the programming. All right, so we have this. Okay, so if that is now the number of steps within that interval, oops, page 135, the new time interval becomes what? So where each time step subinterval is delta ts will be equal to the delta t divided by ns, okay, the one you had. Okay, so now this is the part that you don't need to do the mistake. So now you have this, and now what you need to do is calculate. All right, you need to calculate or estimate the yn plus 1 value using the delta ts within the sublevel. Okay, so basically, let's say you were here at time step 5, 6. Okay, now you created here some subintervals. All right, so it would be this and s. Now you need to recompute using Runge-Kutta. You need to find the values over here. Okay, all right, so you need to redo. Now you have the values here, here. Now you need to recalculate the values here, 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 and here using the Runge-Kutta. Okay, depending on the number of points. I think in most cases only 1 point in the middle. You divide this by 2. But if that doesn't work on the first iteration, you might have then this and 5 and so on and so on. All right, and remember to perform validation at each time step. Okay. Okay, so let's go now to the assignment part. So you need to program this. So I'm going to do this. First, I'm going to put the assignment, and that way it will be easier. So this will be the end over here. Now let me go here to assignment. To the assignment will be test. So first will be write the MATLAB code for the Richardson extrapolation method, and 2 will be test the method for the following initial value problem. So the initial value problem is dy dt, so I put in general form, equal f of yt, where fy of t, I'm going to say, will be equal to minus 5 t to the fourth y squared. And you know that the initial condition y of 0 will be 1. This is our initial condition. So this is our initial value problem. So obviously here I'm going to give you the exact solution, okay? But in order to solve this, let's say let t final to be equal to 3 and n equal to 10. So that's the total number of points. And I'm going to put here experiment with different values of the tolerance. So let's say I'm going to put this equal to 0.1, 0.01, and 0.001. Okay? So an experiment with different values of the tolerance, and there's a lot of n's in this phrase, and different values of n. So let's say n will be equal to 10, 20, and that's it, 10 and 20, okay? And let's see what happens. So let me give you the exact solution. 136. So for comparison, purposes, the exact solution is what? Y of t is equal to 1 over t to the 5th plus 1. Okay. All right, so we're a little bit done with this. So now I'm going to switch here a little bit into MATLAB, okay? So I'm not going to show my code, obviously, but I'm going to show the result, basically. So if I come over here, let me come over here and maybe open that window as well. Let's see if I can minimize this one. That one is not that important. So basically, this is the Richardson method. You see t initial is this. Let's say t final, I put 10 over here, so let's change it to 3. N equal to 10. And the tolerances are 0.01, 0.001, so this will be, maybe I should put here, 1, -2, -3. See, I was testing different cases, and -3. Okay, so now obviously this is just the figure. What I'm asking you to do is this function over here, all right, that I call this one in my case. So if we execute this, okay, so you see that takes a little bit of time. All right, so let's maybe move this to different tolerances. Oops, what am I doing? It's not what I want. 2 here and 1 over here. Okay, that's basically what I'll be able to do to switch from one to the one, from one to the other one. So this will be tolerance 0.01. You see this function in blue is the exact solution, and this is the 10 points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you needed to do one interpolation, one adaptive interpolation somewhere over here. Probably is in here, okay? One of these points. And this is exact, so you see it's not bad at all. But when it was the rapid change over here, wasn't able to capture it, okay? So here you will need more points, basically, and here's pretty good though. All right, but you see, initially the change is a lot more abrupt than is recovering over here. And if we go to the second tolerance, 0.01, you see this time it's about the same number of points. So there's not of a big change at all. So it looks like this one and this one are almost identical. All right, let's see if we have a chance with this one. This one is creating more points. So this one not changing much on the tolerance. You see this one now is creating more points in between. And it goes still over here is not perfect, okay? So maybe this is not enough. I think that's probably why I change here the tolerance. So let's say here we put, let's do the same as before because there's no change between these two over here. 3 and 4, which is what was before, and let's rerun it. And now basically you see it created all more points on top, and now it's almost equal to the exact over here, okay? This, all right, this one, you still have more points, so this is actually the best one we had before, created more points, and this was the initial one as before. So, okay. So basically, maybe let's go back here to this problem over here. And since I gave you some of the answer, maybe just change these tolerances over here at the bottom to make it more significant. Change into 0.01, 0.001, and 0.0001, okay? Instead of these values. Otherwise, you're going to get twice the same curve. All right. Okay, so now I can do this over here. Let's go back to the MATLAB. Over here, and these I have not tested. Let's see what happens if we go, what is the next number of points? 20. what happens over here. Alright, so now you see you take more points, so it will be a lot more accurate, okay? So it's just more points, so with more points, even the tolerance 0.01 is accurate enough. And if you want, I didn't put it, but if you want, you can calculate the residual for this one and actually find out if there's really any difference, okay? Once you put the different tolerances. Alright, so obviously what you need to do is this RK4, but I'm not going to give it to you directly. What I'm going to do instead is I come here. This is Dr. Devo MATLAB code. So this is, you see the function with the initial condition. This is the exact solution for a final time step of 3. This is for 10 points, so this will be the time step. And this is the solution that, I don't know if that's the exact or the other one, but basically what you need to do is that I give you the code over here. I will attach this to the notes. You see, start at 1. You first do the first time step, will be delta t. You calculate, you see your k1 in function of delta t1. So delta t1 will be delta t. You calculate everything. You find your first estimate will be, this will be the y, n plus 1 with the top 1 on top. This is the first estimate. Then you do your second estimate. Now what is your time step? For the second estimate is half of the previous one. And again, you calculate k1, so it will be k1 2, k2 2, k3 2, and so on, and you find y2 of 2 at n plus 1 equal to this. Now that you have this, you can estimate the error method, the error in between. So remember that equation was 2 to the n plus 1 divided by 2 to the n, y of 2, which is this one, minus y of 1, that is the one that was just calculated on top. This one over here. Okay? So far it's pretty easy. I mean, this programming is not difficult. So now what happened? You can calculate, this is your error. Now you calculate what is the error of the tolerance. So if the error is less than the tolerance, okay, you calculate the delta t max. And let's see what happens over here. So if the error, basically if the error is less than the tolerance, okay, you just go and apply this equation here. In the other case, what I call else, what you need to do, you need to divide the time interval into getting the new time interval. So the new ns will be, you see, you need to take a natural value for this one. So you take the floor, same command in MATLAB, you type floor of this plus 1. This will give you a natural number for the number of steps. So the new time steps becomes what? Delta ts new is delta t over ns. Now you see, this is the same thing as redoing the Runge-Kutta, the traditional Runge-Kutta, but at delta ts. So that means now that at each sub-level, you are going to be able to calculate what will be your yn plus 1. Okay? And that's what you do. So, and then if here goes, you go back to the beginning. It says return. You see this long line. So in this case, you will take whatever value you have at the time step. Next time step, you go over here again. You calculate your first estimate, second estimate. You do the error method. If you don't need adaptation, you use this expression. If you need adaptation, you need to calculate the delta t max. And again, make the sublevels, calculate the value at each one of the sublevels, and you keep saving all this stuff into a matrix yn plus 1. And again, over and over until you get to the desired time of delta t equal to 3. Alright. So basically, I don't know how much time we have on this. Let me see if I can find out the time. This is the software that I'm using. Oh, okay, here we go. So we have 50 minutes, but I think I'm just going to cut this class short, and I'm still going to do for today's class another video, and I will just add it, okay? But I don't want to start something in the middle and then just leave it. I just don't want to start something and leave it like in the middle, because for 20 minutes we're not going to have time. So please start working on this. The programming is not really that difficult, but if you have never done it, it's going to take you some time. But really just follow what I just told you on the notes, especially when you get to this part over here, okay? Because to tell the truth, this is exactly what I did on my program. So basically I calculated y1, y2, and then I say if delta T max calculated with this is higher than this, just go to this. Else, okay, every other case which doesn't satisfy this one, what do? You need to go to the adaptation. So in that case, the new number of time step is this one, and your new time step is this one. And now what I do actually is that I don't even rewrite those T1, T4. I just using the time step between the 2 points of the time step, I call our ODE function 4 to calculate the values at each one of these points. Okay? So that's really the way I did it, but you can do it any way you want. So this is the assignment. So this probably will be just an assignment by itself, because I don't want to add problems that might be related to this, because if you don't get this one, you won't be able to do the other problems. So this would be the assignment 2, and let's say the due date for this one might be pretty quick. I mean, if you are good at it, it's just going to take you 10 minutes. If you're not good at it, it might take you a couple of hours, okay? But let's make the due date today's Thursday. So Thursday, March 26, 2020. Okay, I'll create right now the link into the assignment into Canva so you can upload it. All right, so basically what I want is I want to see you need to attach the MATLAB code. That's really what I want to see. Plus, let's say, what do we have for n equal 10? All right, you need to attach three figures, basically one figure for 0.01, one figure 0.001, and one for 0.0001. Okay, and then to do the same, do the same for n equal 20. All right, and basically I want you to do that because assignment 3 basically will be to solve different first order differential equation using all these different methods so that you can compare each one of the others. All right, again, since we have about 10 minutes, let me just add one thing which I'm probably not going to do with you, but at least I want you to be aware, is that you're actually doing right now the work for MATLAB, okay? Because MATLAB itself has some functions. So let's see if I can find them. All right, yeah, here it is. So let's say we wrote down our function, remember, ODE1, ODE2, ODE2H, ODE4, and now let's say you're going to write down your ODE for Richardson. Okay, so MATLAB itself, they have their ODE. You see, ODE45, which is most of the time. Basically, this is order 4-5. This is kind of the same thing as the Richardson methods that we do, but instead of being the Richardson method, is one called the Fairberg method. Okay, ODE23 is kind of similar to our EUNS methods, which is the ODE22H, all right? But you see they have their method, and they have different ones. You see 1.5 and so on and so on, and they tell you when to use it and the accuracy level. But basically now, since you have wrote your own functions, it's a lot better because you know exactly what it's doing. But you can still use these ones, and basically the way to use these ones is very similar to the way we have been doing ours. Okay, if you need some help, you want to use these ones, all you're going to do, I will attach this. This is the MathCAD from Dr. Diva. I will also attach it to the notes, to the video of today. I'm sorry I cannot attach right now the lectures, but I don't have a scanner. If I go by school, I promise you I will scan the notes and I will add them to the videos, okay? But I'm not going to school for the reasons that you know. So we have this. So if you go here actually to MATLAB and type help, I guess ODE. Okay, so maybe help ODE45. You see it will take you to a document over here, which basically is the same thing. You see the solution is ODE45, where the ODE function is your function, the F that we use. T initial, T final, you see a little bit different. You need to put in between bracket, and then this will be the initial condition. Okay? And they give you an example. If you want to use it, go ahead. You see they have all this stuff over here. You can play with them. But I'd rather have my own code to know exactly what it's doing. Alright, so I'm going to terminate this video here, but you can expect another video coming very soon, probably today, about moving to the next section. Alright, so let me close this. So thank you for your attention, and have a nice day. Let's see where I can close this. I don't want to pause. I actually want to finish this. So, okay. Alright, I don't have that screen showing up. Alright, sorry for that, guys. I'm just trying to close this, but I don't find the stop button. The button for stopping it. So record is recording. I don't want to pause. Okay, let me. Alright, I maybe don't want to pause. I want to finish it, but